Okay, let's get started. Welcome everybody to the next edition of Canvas. And today's speaker is Doug Johnstone from the NRC Hertzberg in Victoria, who will be talking to us on an interesting subject, variability of embedded protostars. Doug got his bachelor's in 1989 from the University of Toronto and then a PhD in 1995 from the University of California, Berkeley. Doug is also an adjunct at UVic as well as his position at Hertzberg. So real pleasure to have Doug share some interesting work that he's been pursuing, and take it away, Doug.
Excellent. Thank you very much. And thank you for the invitation to talk to you and talk to all of you about the variability of embedded protostars and what it tells us about their mass assembly process, how they accrete, and gets an opportunity to try to understand the physics of what's actually going on during the evolution of a protostar. As Dennis has already said, I work at NRC Hertzberg as well as an adjunct position at the University of Victoria. And the project I'm going to talk to you about is primarily done at the JCMT in Hawaii. And I'm very pleased to say that it's a big international team and that it's predominantly being graduate students and postdocs getting to lead and write what I think are some very exciting papers. And I hope you enjoyed this as well. Let me start with a brief acknowledgement. As somebody who works at the University of Victoria, I think it's important to acknowledge with respect the Lekwungen peoples on whose traditional territory the university stands, and the Shanghaes, Esquimalt, and Saanich peoples whose historical relationships with the land continue to this day. Furthermore, up at the observatory, working at NRC Hertzberg, we also acknowledge with respect that the observatory is located on the traditional territories of the Coast Salish peoples. And then, as hopefully all of you are very well aware, the James Clerk Maxwell Telescope at the East Asian Observatory is in Hawaii, and we wish to recognize and acknowledge the very significant cultural role and reverence that the summit of Mauna Kea has always had within the indigenous Hawaiian community. We are fortunate to have the opportunity to conduct astronomical observations from this mountain. So let me just start with a really brief background why variability. And if we teach our undergraduate students the fact that most of what we do in astronomy comes to us as light. We are either measuring how bright something is, what color something has, spectral features, but the time domain also gives very important information. If we can measure the period, if we can measure the amplitude, if we can measure the Eigen-frequencies, we can deduce things about the object that we are studying. The most obvious one is the density by looking at pulsating variables, as well as internal structure. In fact, there's an entire area of astronomy referred to as stellar seismology, where they do just that. And once you know these stellar properties, of course, you can use objects as standard candles, as we often do, or you can try to probe the physics that's going on inside, such as trying to understand convection zones inside stars. So all of these are reasons why we're fascinated by variables and why the time domain is becoming an ever more important part of how astronomical research takes place. The complication we have when we're trying to do this for young protostars is that they're enshrouded by their prenatal envelope. And so this picture I have on the right in the optical and infrared, this is a little bit of a fake in that I'm actually showing you a prestellar core, not a protostellar core. But even in the prestellar core, you can see in this optical infrared image just how much reddening there is as you get into the core that eventually is going to form a star, and you basically get ever harder to punch into the center of the region to actually get the emission that's coming if there were a protostar in there. However, if you look at that same region in the submillimeter, you're looking at the warm dust, in fact, the very same dust that's doing the enshrouding and that is absorbing the photons that come in the UV and the optical is emitting in the far infrared to submillimeter. And the submillimeter is what we can observe from the ground. So this is the whole idea behind our observations is we're going to look in the submillimeter and see what we can get. So we started this survey 4 years ago, looking at 8 regions in the Gould Belt, 8 star-forming regions in the Gould Belt. We got a 1-year extension, and then just recently we were renewed for another 3 years. So the survey is now halfway through, shall we say, a 7-year set of observations. Within these 8 regions, we're following about 200 protostars, 800 disk sources, but you've got to be a little careful as to how you count those, because of course some of them are faint and some of them are bright. And we have a 1-month cadence, which I'll come back to in a bit. First, however, I just want to focus you on Serpens Main, and I want to tell you that we're very excited. When we first put this survey into the JCMT, it was highly ranked, but we actually had the suspicion we might not measure anything, and we might only be producing an upper limit. However, less than a year into the survey, I got a nice email from the Korean PhD student, Hyunju Yu, who was studying Serpens Main, and she had found that one of our sources was actually varying. It was going up in brightness, and she had done her due diligence, but first let me show you the light curve. Here's the light curve of this source. And so here it was over the first 6 or 7 months of the survey, and then suddenly it brightened. It brightened late in the fall. And then, of course, as all good objects do, they go behind the sun, and you have to wait till they come out on the other side. And it was even brighter and dropping. And in case you're worried, because you should be, that measuring brightness in the submillimeter, how can we be so certain we're actually measuring what we are hoping to? Here are 2 calibrator sources in the same field that we're following, and on the same scale on the y-axis. So you can see the calibrator sources stay very stable, but EC53 clearly rose and then started to decay again. Well, Hyunju Yu did what any good graduate student should do when they find an object that's doing something interesting. She went to Simbad, looked up the location of the source, and found that it was actually a known near-infrared variable with a 1.5-year periodicity to it. And here we did a very simple folding to show that, in fact, the fold worked relatively well to say that maybe this was going to be periodic in the submillimeter as well. Interestingly enough, the source which is being followed in the near-infrared, that source, EC53 or V371 Serpens, it's being followed because Klaus Hodap is not interested in it, but interested in the source nearby, which had undergone an Fiori powerful outburst about 10 years ago, and he's been monitoring to see if it will outburst again. So there's a lot to unpack here, and we'll come back to much of it. But for the moment, suffice to say that we've been able to show within 8 months of the survey that, in fact, we can catch variables in the submillimeter, and that variability has a connection to variability that you might see at other wavelengths if you can actually probe the protostar at those wavelengths. Okay, so let's now take a little bit of a step back and remind ourselves what we're really trying to do here. Okay, this is a slide that shows you how we think a protostar is formed. You start with a dark cloud. It has some dense patches in it. Those dense patches become either massive enough or get shrunk enough, or they lose their turbulent support or lose a little bit of magnetic support, such that under their self-gravity, they decide that they want to collapse. And so then they're going to collapse down towards the center. Anything that can break the symmetry, and we'll come back to that, will lead you with a disk. You get a bipolar outflow because you got a lot of energy, not all of which can get absorbed by the central source. And so you basically power out these bipolar flows. And then as time goes on, the envelope dissipates, either because it runs out of material or because this bipolar outflow and the radiation from the inside pushes the material away. And then you have just a star with a disk around it, and then the disk we expect to break up into structure and basically form planets, and you end up with a solar system. And one of the things you've heard a lot about in the last while is whether or not this breaking up into planetary systems happens late, or whether it may actually be happening earlier in these systems. Now with ALMA, we're seeing structure in the disks. I'll come back to that. But the part that we're interested in right now is this assembly process of the star, where the material is falling down to the star and trying to build up a star. Now, as that material falls in, it has to give off energy. It gives off an accretion luminosity as all of that potential energy gets converted first to kinetic energy and then to luminosity through shocks. And it turns out for the very low mass protostars that we're looking at, the typical solar mass or so protostar that we're looking at these early stages, all of the energy that we see is due to accretion. Okay, it's either reheating of the interstellar radiation field if you're in the outer part of the envelope, but if you're in the inner part of the envelope, it's all accretion luminosity. And that accretion luminosity can't come out in general because of the enshrouding of the source. And so instead it gets absorbed by the envelope, the dust in the envelope, and re-radiated at longer wavelengths, such that if you're a very deeply embedded protostar, you have an SED that peaks at maybe 100 microns and then goes on out into the submillimeter. And then slowly as that envelope decreases, you get to see ever more of the shorter wavelength radiation getting out, and the source starts to become observable in the mid-infrared, and then eventually you actually get to see the star. So we had discussed back in 2013 that this process should allow us to use the far infrared and submillimeter as a proxy for accretion, because what we monitor in the far infrared and submillimeter is the response of the envelope to the accretion at the center, which has to get out. And so that's what we're going to try to do. And the first thing you should think about is, why would it vary at all? Why would we expect there to be any variation in the accretion? This is a process that's taking 1 million years, 100,000 to 1 million years to build the star. So let's again take a step back and think about that clump that is collapsing. And the simplest model that you can come up with, which probably isn't right, but it's a nice simple model, is the isothermal sphere. And the isothermal sphere is a static equilibrium object, but it is not a stable equilibrium object. It has a very, very simple density distribution, which is entirely determined by the sound speed A. There are no free parameters. Once you put the sound speed in, you basically have given the calibration of the density, and it always goes as r to the -2. If you take that equilibrium situation and you just remove the material down at the center for whatever reason, then that takes away the pressure support that holds up the outer shells, and the outer shells start to fall in. As they fall in, a refraction wave goes back out through the envelope at the only speed it knows, which is the sound speed in the system. And so you've got a refraction wave racing out at the sound speed. You've got a surface area that grows as r squared, and a density that's dropping as r to the -2. You put all of that together, and the mass infall rate is a constant. It's a fixed value. Now, and so that means that the isothermal sphere, as it collapses down at a very fixed rate, and you get a very fixed mass accretion with time. Now, in reality, it's probably not that simple. There's more structure. An isothermal sphere doesn't actually exist. Bonner-Eberts and the like are better, but all of these models basically have a smoothly varying in time mass infall rate, okay? And so this is what we assume is happening, and it works, sort of. And that is, if you put in a sound speed here, which is typical for a prestellar core, let's say 10 Kelvin or the like, you basically get a mass infall rate of something like 10 to the -6 solar masses per year, which means it takes you that 100,000 to 1 million years in order to build your star. So what's the problem? Well, the problem is when we actually go out and we observe protostars, we find that they're underluminous in general. That is, remember I told you, once I know the accretion rate, then I should actually know what the luminosity is from that central star, because it's all falling down onto the star. So I should be able to plot, like these blue lines, how bright the star should be as it moves through its various phases, gaining mass, both because of its own mass and the accretion. And yet when we observe them, these red dots are typically much lower in luminosity than we expect the system to be. If you do it as a histogram, you're somewhere between 1 and 2 orders of magnitude too faint compared to what you think you should get for a protostar that is forming. So what's going on here? Well, I think the right answer is there's a disk. And I think we all recognize that it's the disk that is causing the difficulty or the change in the situation, because that material doesn't actually hit the star, it lands on the disk. Anything that breaks the symmetry means you're actually going to land on the disk rather than land on the star. And once you get onto the disk, you got to figure out how to move through the disk. You no longer have free fall working for you because you landed on that disk because of angular momentum or because of the magnetic field line. You now need to have some viscous property that basically allows material to slide past one another and move into the central region. And in general, one would expect the disk transport mechanisms to be slower through the disk than they are through free fall coming in. And I just want to point out, and one of the main motivators for our survey is that there are a lot of theories for disk transportation, for how to move material through the disk, but there are very few observational constraints. Almost everything comes from the ideas there are of how ionized or how warm or how dense or what type of perturbations you can actually build up in the disk. And I also should note that there's no reason a priori to believe that the disk itself has to transport material smoothly. So people have worked on this. Lots of people have worked on this process. Shantanu Basu at the University of Western Ontario with Edward Drobyov, when he was a postdoc there, made models where they had material fall onto the disk, but basically made it unable to move through viscous processes. And instead, their disk would get massive. Once the disk gets massive, it gets gravitationally unstable with the central star, wiggles back and forth, builds up spiral arms, and then the spiral arms are an efficient way of transporting mass, and they would get these bursts. These are mass accretion rates. They would get these giant bursts of accretion, which we think of as being like F-Uri events, where the star suddenly bursts maybe 100 times brighter than it was before. And there's some evidence in the outflows that we see from protostars that they may have had such giant bursts in the past. You can see that they tend to be very symmetric with bursts going out on both sides. So that's one possibility, but these are giant bursts taking long time scales between them. You can see this is 10,000, 20,000 years. These time scales are thousands of years in between events. We're going to be looking on shorter timescales, but the other thing that we're also aware of is that the disks themselves are structured. When we look at young disks these days, whether we look at them with scattered light from near-infrared adaptive optics, or whether we look at them in dust emission, and these are somewhat older disks, I will admit, but when we look at these disks, we see structure to them. And in fact, the biggest thing we see in the structure is we see lots of radial profiles, lots of ring-like profiles, which suggest things like planets in formation, but we see these rings around young disks, and lest you be worried that ALMA has only been targeting a very special set of disks, which are the ones that look like this, Beijing student Feng Long, in a survey we did with Greg Hergzeg, did an unbiased survey with ALMA of T-Tauri stars and Taurus, and found that 1/3 of the T-Tauri stars had disks that had large scales to them and had lots of structure in them. So this is a common occurrence that's happening. The disks around stars are structured. Okay, so let's go back one more time. Think about what's going on in this phase here where the material's coming in. We're not going to have it go to the star. We're going to have it go to the disk, have to move through the disk and accrete onto the star. What might I be able, how might I be able to probe this property and use the submillimeter to understand what's going on? So graduate student at the University of Lancashire, Ben McFarlane, for his PhD thesis in 2019, built numerical simulations of a core collapsing down to the center so that he could watch the 3D structure as this thing collapsed down, how it built a disk, how it produced a bit of an outflow. And what he did for us was he took his models, kept the envelope and the structure the same, but varied the accretion luminosity at the center of the region and watched how that would affect what the SED would look like, what the spectral energy distribution would look like. And perhaps, as you might expect, if you make the luminosity higher, the system gets ever bluer as it gets warmer. But the submillimeter response, which is over here, is much weaker. You can see it better here where he's plotting them against each other. All of these are plotting the various spectral energy distributions against the dashed version. And you can see that in the submillimeter, we get a response, but that response is weaker. It's more like a temperature response because we're getting closer to the Rayleigh-Jeans part of the curve, where the luminosity that we see or the brightness that we see in the submillimeter scales as the temperature. As you move into the far infrared in particular, you're basically picking up the accretion luminosity itself because you're at the peak of the SED. And then you can see as you move into the mid-infrared and the near infrared, it gets really messy because it all has a dependence upon where the optical depth is, how optically thick are you, and then how are those photons getting out. Because of course, especially in his model with 3D, those photons can get out in different directions. Okay, so Gazan Baek, a Korean PhD student, took this one step further, and she's using two-dimensional SED models that are much easier. They're not the complicated three-dimensional collapse, but they allow her to fit to an opening cavity angle, the envelope size, the importance of the disk. And she did this work for our variable EC53, where she had to fit not only at one location in time, but in all the locations in time, the various brightnesses. And what we find is that the SED now that we have, we can break a lot of degeneracies that show up in these models by doing this, because when you're varying it, you've got yet another parameter to sort of watch. And so she was able to get us a good measure of the envelope size of EC53, the cavity opening angle of EC53, and a better idea of when we see a variation in the submillimeter, what's it telling us about the underlying luminosity. So if we can do that, this tells me that observing here in the submillimeter is a good proxy for the accretion that's going on, even though it's a weaker proxy because I'm only measuring a sort of temperature effect rather than a luminosity effect. So that's what we think is happening. The other question you have to ask is, if I do change the luminosity of the central source, how long does it take for the envelope to be aware of that? How long does that response take? In other words, is it short? Is it long? What is the time scale? And it turns out that dust has no heat capacity. Because dust is small and fairly rigid at these low temperatures, you can put the energy in, but it doesn't have any modes to go into. And so the dust has a very low heat capacity. It basically warms right up or cools down when it's no longer being heated. People who've ever looked at very small grains, which get superheated and then get cold, understand this phenomena very well. And so it means that for the envelope, the ability to observe it with, let's say, the JCMT, which observes the whole envelope, the time scale that we're looking at is the crossing time to the size that we're interested in. And so if we're only interested in, let's say, the near infrared or the mid infrared at the scale of the effective photosphere of the envelope, where it's really warm down at 50 AU, the time scale is only 6 hours for the envelope to respond. However, in the submillimeter, where we're basically looking across the total system, the size scale is more like 5,000 AU, and the time scale that we're interested in is about a month. And this is what set the cadence for how we did the observations with the JCMT. So one more bit, do we expect to see variability? I've already pointed out that we're under luminous. I pointed out that there are F-Uri type events. And in a study by Will Fischer and his student using Spitzer and Wise data, they found 3 objects, the McNeil's Nebula, HOPS 383 and HOPS 223, that had gone, that had changed in brightness significantly by factors of 10 or so over 7 years between when the Spitzer survey had been done and the Wise survey had been done. And so they basically used that to again argue that over time scales of a few hundred years, all sources probably undergo events that drive at about a factor of 10 in luminosity. Again, we don't want to wait 500 years. We don't have that type of time. What we're curious about is if I relax this assumption and say, what about small brightness changes? Can I see small brightness changes on short periods of time? And do those brightness changes give me any hints at the physics that's going on? And so obviously, I think the answer is yes, or I wouldn't be here talking about this. So let's now talk about the survey itself. Okay, so we decided to go out and look at 8 regions. The 8 regions were purposely chosen to be regions where there was a lot of submillimeter emission and there were a lot of known protostars, okay? And so as I said, we chose a 1-month cadence because that's what we expected for how long the envelope should take to respond to anything going on. The biggest problem that you have is observing with the JCMT is tricky. It's a submillimeter telescope. It's a big dish. It doesn't have particularly good tracking. And so you can see on the image on the left, this is the default alignment calibration that we get from the JCMT. And if you've ever observed in the submillimeter, you know that we typically take the flux calibration to be 20, 10, 20, 30%. Which is horrible if you're going to be looking for sources that have only varied a little bit. Fine for those Fiori bursts that are big, but if you want to look for small bursts, this is going to be a major problem. So PhD student Steve Mayers, for his 2017 PhD, the last papers of his PhD, he came up with a technique to use bright sources in each image to align the data, getting us alignment better than about 1 arc second. The beam of the JCMT is 15 arc seconds, so that's not bad. And you can see just how much better we are than what the JCMT gave us as a default. And he also came up with a bootstrapped technique to basically find sources in the images that weren't varying and then use those sources as relative flux calibrators. And that was enabling us to get from an 8% uncertainty at 850 microns that you get directly from the JCMT and bring that uncertainty down to about 2.5%. So this was a very exciting result because we didn't know we could get there. And we basically were able to bring things down by about a factor of 3. More recently, University of Victoria undergraduate student Colton Broughton worked with me as a co-op student up at the observatory and has since been working with me through my discovery grant at the university. And he's using techniques that the optical astronomers often use, autocorrelation and cross-correlation techniques, which allow us to align our maps to better than 1/3 of an arc second now. And we believe that we're getting a flux calibration even better than 2%, with the caveat that we actually have variables in our images. And so these the autocorrelation technique that we use for the calibration actually has the variables in it. And so we somehow now need, again, to bootstrap to remove the variables. And that's the work that Colton is doing as part of his undergraduate thesis. So what do you get when we're done? We get these beautiful calibrated light curves. And across the top of the image here, I show you 3 sources that are varying. And in the bottom of the image, I show you 3 sources that, well, there might be some variation. We don't have any robust measures because the sort of dotted lines here from the mean are telling you the sort of standard deviation, 1 sigma in an individual measurement. And so we've got lots of sources, most of them deeply embedded protostars because that's what we're looking at, the submillimeter. But if you actually start going and looking at them not just as an ensemble set, but you look at them as individual sources, you find that they're intriguing. Here's HOPS 383. It's one of the sources that Will Fischer pointed out when he looked between Wise and Spitzer, and we now, where he had seen it do a brightness increase, and now we're watching this source slowly fade away. There's the source IRAS 18270 in Serpens, which is also slowly decaying. And when you go and you look in the literature, you find that Connolly and Green looking at its mid-infrared lines, in particular molecular hydrogen lines, found that it had line emission that was reminiscent of an Fiori candidate. And then finally, here's one that we saw decay very dramatically, but at first we thought it was actually a prestellar core, and we're very nervous because prestellar cores shouldn't vary, but it turned out it was misclassified in the original tables, and Amy Stutz reclassified it a Pax bright red source, which meant Spitzer saw it as a very, very red source, initially thrown out because they thought it was a background galaxy. But these Pax bright red sources, and there are many of them now, Amy believes are actually very deeply embedded protostars, quite possibly the youngest, although that's still to be determined. And then here's a source that caused us much grief. Again, another Pax bright red source, but this one was stable for so long, we were using it as a calibrator, and then suddenly it started to dip down. And the reason we knew it dipped down wasn't because we saw it dip, but was because we saw every other source in our region start to jump up. It became much, much brighter. And so we had to go back and look, and sure enough, one of our calibrator sources was no longer a good calibrator source. So we had to take it out of the survey, or out of the calibrator list. Okay, so now we've got a whole bunch of these. We've been observing for 50 months. As I said at the beginning, I don't want to just see that I've got variables. I want to do some physics with them. And so the best way to do that is to try to measure and try to fit things to the data. And the two obvious fits to try to make are linear fits and sinusoids. And so here on these 6 sources, I'm showing you the best fitting linear fit, which is a dashed line, and the best fitting sinusoid, which is the solid curves that you're seeing on the plot. I'm not trying to tell you that they're good fits. I'm telling you that they're reasonable fits, and they're fits that we think we can get some physics out of. And so let me explain. So the first thing to do is to recognize that when you try to fit sinusoids, the best way to do this is to try to use these periodogram analyses where you run through all the possible frequencies that you can, and you look at how good a fit, which is basically how much did you reduce chi squared when you put the best fitting sinusoid with that frequency. So here's a really poor fitting sinusoid. And so you can see it has a very low power. Here's not a bad fitting sinusoid, and it's at a very, very long period, but it has a pretty good power. And then here's a really good fit to this data set. And you can see it comes in at about 1.5 years, which is exactly what you expect, because this is EC53, and that 1.5 years is what we got looking at it in the near infrared. And so this is the work of Korean PhD student Young-hee Lee, who visited me and luckily got away just before the pandemic closed everything down. And here he is in my office talking about how we're going to put this paper together with our co-author, Greg Hergzeg. And so when we do this analysis, we can look up here at how strong this power is, and we can use that to come up with a false alarm probability. And so what you want is you want something that has a very low false alarm probability, such as EC53, to convince yourself that indeed you're looking at a source that is varying, let's say, sinusoidally. And so when I put this dashed line along here, I would say everything above that dashed line has a really good chance of being actually variable, and everything below that dashed line is much less certain about whether it's variable. It could be varying, but at a much lower amplitude, so we can't detect it yet, or it could be static. The key thing I want you to go away with is that we see starless cores and we see protostars, those are the blue and the red, and we see them all across the flux values, but we only see protostars in the top of this plot. Now, the very observant will note that there are 2 blue dots in the top of this plot that say they're starless cores, but both of those are sources that were misidentified. One of those is our source HOPS 373, which we mentioned already. The other one is a source called Karma 7, which was again so deeply embedded that it was missed by Spitzer, and so it wasn't in that proper catalog, and we had to find it after we found it as a variable. So it's really nice to know that the only sources that are varying are the protostars, which is what you would expect. So what else can we do with this? Well, the bottom line here is that we've got about 24 bright protostars that are showing secular variability. And those 24 bright protostars are out of about 60 bright protostars. We have about 180 protostars in all, but most of them are faint. And so it's only these 60 that are bright. So now the question is, we've got a bunch of protostars that are varying. What can we do with that information? How strong is the variation? How long does the variation take? And which type of stars are varying? All right, so the first one, here I'm plotting the period of the variability as determined by the periodogram analysis and the fractional amplitude. That is, how big is the amplitude compared to the brightness of the protostar itself? Okay, here's our source EC53 at about 1.5 years. And then you can see there are a whole bunch of sources that are coming in with periods between 4 and 12 years, let's say. And the interesting thing there, of course, is we've only been observing for 4 years. So we don't have good periods for these sources. But what we can say is that they're large secular variations want to be over extended periods. They want to be over something larger than 4 years for that variation that's going on. And then we have a few sources that are varying so smoothly that they actually want to have very, very long periods, meaning they're basically best fit by a linear function, not by a periodogram analysis at all. But this is actually very interesting because, as I've said, over 30% of our protostars are varying, and the vast majority of those are varying on long, by the timescale of a graduate student thesis, shall I say, they're varying on long timescales. The timescales are many year timescales to perhaps many decade timescales. And only EC53 at the moment stands out as a short period variable. Okay, can I do anything more? Yes. The one more thing I can do is I can look at which sources are varying of the sources that we are following. So this is a well-known plot that people make in the star formation community, where we're measuring the bolometric temperature, which is basically where does the SED peak, how cold does the source look like it is, and on the y-axis we're measuring the bolometric luminosity. How much energy is that source giving off? So all the dots on this plot are from Orion, and they come from the HOPS survey that Furlan put out. And they're showing you basically the distribution across class or across temperature and luminosity of all of the sources in Orion. The ones that are in blue and red are the sources that lie in the 3 fields that we are following. So all those gray ones, we're not even looking there. But where the blue and red dots are, that's where we are looking. The red ones are the ones we detect in the submillimeter. And it shouldn't be a surprise that we detect most of the sources that are class 0, and then slowly but surely we get less and less as we go into the class 1 phase, because there's less envelope in the class 1 phase, and we're looking in the submillimeter, which is detecting the envelope. So we expect to be dominated by looking at the class 0 sources. The ones with circles around them and are named, those are the variables that we are detecting. And those variables, as you can see, are also highly clustered in the class 0 phase, with the exception of V1647 Ori, which is again a well-known FU or XOR source. And so if we do our numbers, we find that 17% of our class 0 sources are varying. And what we'd really like to know is whether these are the stronger variables, whether these are the shorter timescale variables, and the like. But that requires us to understand our selection effects much better than we've been able to. And that's, in fact, what we're working on for the paper that we're going to try to put out by the end of the summer. Okay, so these are all the things I can do, and it's early days. We don't have all of the final details yet, but what else might we hope to do? How can we actually really get at physics? Let's go back to the spectral energy distribution that we get from the fact that we've got this accretion onto a protostar, a disk, and then onto a protostar, and then getting out through the envelope. Can we learn anything more from the data set that we have? So remember, I told you that PhD student Ben McFarlane was making these models, and he was showing us that when the luminosity changed, you got a different response in the submillimeter, more of a temperature response, compared to what you got in the infrared, where you got more of a luminosity response. So what happens if you go out and you try to investigate that? we basically took our sample of submillimeter sources and collated them against the WISE satellite, which has been up in space doing the NEOWISE survey now for about 6 years, taking data twice a year on all of the sources in the sky. And so we could find the sources that we had in common, about 50, find the sources that were clearly varying, we had about 12, and when they were varying both in the JCMT and at WISE wavelengths, which is 5 microns, say. And what we found was if they were getting fainter in the JCMT, in the submillimeter, they were getting fainter in WISE. And while I don't show a picture, when they were getting brighter at the JCMT, they were getting brighter in WISE. Not only that, you can see here, and this is in log, you can see here some more like magnitudes, that the response from the JCMT is always weaker than the response from WISE. In fact, you can plot that. You can plot the WISE slope versus the JCMT slope, get a very nice relation with a fit of something like 5.4. Now, this is interesting because at first blush, you might have said the infrared was the luminosity, the submillimeter is the temperature, and therefore you might say, well, the temperature is probably luminosity to the 1/4 power, because that's sort of the relationship that you expect. That would give you a relation of 4, which isn't quite what we're seeing. Well, it turns out when you look at it carefully and go back to those SED fits, you find that the submillimeter is not really on the Rayleigh genes. It's not quite dust temperature yet. And the infrared is not quite on the accretion luminosity, but it's close. But what this is really doing is telling you that the phenomena that we see in the mid-infrared is the same phenomena that we see in the submillimeter, and that they are probing the envelope in such a way as you're seeing the response from a luminosity or the response that it has on the dust. So that's great. That's a paper that a postdoc, Carlos Contreras Peña, put out for us that just got accepted about 2 months ago. So what about our quasi-periodic submillimeter EC53? So while Younghee Lee was with me in Victoria, we were actually working mostly on this source. And again, here's us figuring out what the paper should have. And we just submitted the paper this last week. And what he did is he did a detailed analysis of all of the other wavelength data. So here's our submillimeter data going back about 3.5, 4 years. Here's K-band, H-band, and J-band data that go back more like 7 years, 5 cycles. So he took this data and he tried to phase it all up and made these beautiful light curves in J, H, and K, and as well showed what the light curve, the radial light curve, looks in the submillimeter. Now this is nice because there are a number of things in here that are important. First, when it rises very quickly, and when it decays much slower. So you can see that very clear. The other thing you can see is the submillimeter does what it should when it's at the brightest point, because it is delayed from the near infrared by about a month. But something weird is happening because the submillimeter seems to turn over and start brightening before the near infrared knows that it's going to turn over and start brightening. So this caused us huge amount of grief for actually 3 years, ever since we submitted our first paper, because why should the submillimeter start to rise earlier than the near infrared? This is supposed to be tracing the deeply embedded protostar, and the envelope response is supposed to be delayed. This is a conundrum. But the most important thing that Younghee did was he not only gave you the phase curves, the phase folded curves for JH and K, he also produced the colors at JH and H minus K. And look what happens right as the source starts to brighten. It goes through a dramatic reddening event. While it wants to brighten, the source also gets dramatically redder. Okay? Something is occulting and causing great extinction right at the same time that the source is trying to brighten. In fact, you can make beautiful color magnitude diagrams for the source that show this wonderful hysteresis where the source starts, let's say here, getting fainter and getting actually a little bit bluer, and then it races along a reddening vector, right along the reddening vector as it gets fainter, and then jumps up to a higher brightness and runs back along that reddening vector and then repeats. And what you can see if you look at H in the H band and H minus K, you get the same effect, only it's a little bit flatter than it should be if it were just a reddening event, which suggests that it's not just an extinction event occurring, but extinction at the same time as it is trying to brighten. And you just don't see it in J because the extinction dominates, but because the extinction is less at H, you actually see a little bit of that increase in brightness at the same time as the reddening is also taking place. Okay, so this is complicated, but let's step one more step back first before we explain what we think is going on there. And so here's the actual light curve in time rather than folded, and you can see that it's only quasi-periodic. It's not actually exactly the same timing each time we come into a burst, and that's one of the reasons why those light curves have a little bit of flicker to them. But what you can see is every time it gets brighter, it follows exactly the same slope. And you can find a rise time in E-folding of basically 1/10 of a year. And every time it gets fainter, it follows the same slope. It has a decay rate of 3/4 of a year. There's physics in there. Something is driving those timescales. For the decay, if we associate it with a viscous disk, which is viscously spreading, think of using, an alpha disk parametrization, we can actually measure from this decay rate, we can measure how big the inner disk has to be and what the alpha has to be. And this alpha parameter can run from 1 to 0, and usually we expect it to be about 0.01 or something. And so the fact that we're getting a value of 0.3 is incredibly high. It tells us that inner viscous disk, if indeed that's what it is tiny. That's how you get a small time scale. And it has a huge amount of viscousness. It is moving. It is not just sitting there. It is spreading. And you can actually look at the outer disk. And since we have measurements of the mass and the radius of the outer disk, and we can calculate the mean mass accretion rate through the outer disk, we can estimate the alpha in the outer disk as being completely regular. It's right where you would expect it to be, something like 0.02, 0.01. So the outer disk is doing what it should. It's the inner disk that's doing something funny. So what is a model of what might be actually happening? What we think is happening is that the inner disk gets really massive and all puffed up. And when it's puffed up, we're observing from something like here. And so we observe through the puffed up disk to see the material that's falling on. And that's why we have this large amount of extinction. As the disk continues to accrete, the mass falling in gets less, the disk spreads out, and so we no longer get that extinction event. And then the disk gets really, really thin as it's the inner disk, as it's basically almost all depleted. And at that point, something stops a blockage between the outer disk and the inner disk, and suddenly material rushes across on a very short time scale and replenishes that inner disk. And I must say, we do not have any theory for what this might be, but one suggestion that we had before and that people like is that maybe there could be a planet forming or a binary star forming in this inner zone, which is causing the material to get held up, and then it has to get massive enough, a big enough wall, before it's able to jump across again. And there'd be models that predict something like this could occur. Okay, I know I'm running out of time, but I want to just give you a notion of what actually we think is going on. So this is busy, but hang on with me. In the top panel, I'm showing you an unobscured view of what we think is occurring. In green, we think that the infrared is tracing the accretion, and the infrared brightness goes up very quickly and then decays and then goes back up and then decays. And if that is the case, the submillimeter response should be a smooth and delayed response as the envelope warms up in response to what is happening in the accretion. And so then you get a curve like this red one where you can see it's delayed at the peak and it's delayed at the trough. Both of those are delayed because the system itself is responding with a delay. On top of that, we think we have this extinction event, which is lined up with when the source wants to start brightening. Okay? What happens if I put all of this together and observe the system? Well, what happens is this extinction event causes the near infrared, instead of rising, to first drop because of the extinction before as the extinction starts to come down, it's able to race up. And now we get exactly what we observe. The submillimeter never saw the rise faster than reality, but the submillimeter responds before we can observe it because we observe the obscuration. And then when it gets bright, the submillimeter is delayed compared to the infrared. Now, the really nice thing about this model is it reproduces very well the colors of that extinction event and therefore naturally give you an excuse for why we get this funny business happening at this phase. Okay, so we've just submitted that paper. We're incredibly proud of that paper because we think this is the first time that we're able to actually measure some physical processes of what's going on in a deeply embedded protostar at a very early phase. And we can do it because of the physics that we can get at from the variability. So let me talk about something completely different now for the last bit of the talk. There's another type of variability that we can look for in the submillimeter. We are basically at the top end of the radio spectrum, and radio flares are known to occur on protostars and young stars. And so those are related to basically the X-ray events that you see off of the sun when you get energetic events occurring on a star. And so we were asked by members of our team to look for single epoch energetic events that might be occurring over our survey, because we've been observing for 4 years, every month, 8 different regions. And so Taiwan PhD student Bhavna Lalakan has been doing just that, looking at every epoch, trying to find any flux brightness and see whether or not things change dramatically. And unfortunately, over 10,000 possible events, she was able to show that all of them lived exactly where you would expect them to live if we were just dealing with Gaussian noise. And so nothing has happened in our data set over all of these epochs, which is somewhat discouraging, but at least puts an upper limit on the single epoch variability. Except when we were first asked this question, my former graduate student, Steve Mayers, who's now a senior scientist at the East Asian Observatory, and I should point out, he no longer looks like that. This is what happens to you when you get your PhD. He had gone back and done a very quick analysis, and he found the only transient variable that we have in the survey. Here we are looking in November 20th, 2016. This was all archival data. And then on the 26th, there was a brightness increase, and then it went away. And here's a coad showing you there's nothing there except on that one date. And here's an ALMA image of that same location showing you a nice disk, and this is a binary T-Tauri star. If you look at it across time, you can see that the brightness was very, very low. It's consistent with the noise, except in one epoch, where it jumps up to 500 millijanskis, and it's the same brightness at 450 as it is at 850, which is also incredible because usually at 450 you're brighter because of that Rayleigh genes. And so this again suggests that you're looking at a non-thermal source. Finally, because we have so much signal, we can break our 30-minute observation into 5-minute chunks, and we can watch the source decay 50% in flux in half an hour. So this is a very short decay. It is not a large object. It has to be small. It has, in order for it to be able to cool that quickly. And so what we think we're looking at here is a flare. And if it's a flare and you compare it to the sun, it's 10 to the 10 times brighter than the typical flare on the sun. In fact, it's the most powerful radio flare that we have found from any young protostar observation so far. So it's very curious to know whether it's connected to the fact it's a binary, or connected to the fact that it's a disk, or whether it just was a unique, interesting event, but it's the only one that we've found. So in closing, what's next? We're going to continue the JCMT transient survey for another 3 years. We're getting the 450 micron data out now with Steve Mayers and UVic undergraduate Colton Broughton. We're looking at structure function analyses as another way to try to understand our light curves, like the AGN community do, to try to see if there are timescales. And I just hired UVic undergraduate Spencer Plovey to look into that with me this summer. We're working towards CCAP Prime as a survey telescope, which will have a higher sensitivity, get us to higher frequencies closer to that far infrared peak, and it'll have a larger field of view. So we've been working to help plan for a 350 micron camera, and UVic undergraduate Kayla Douglas is working on me with to try to find effective and efficient scanning techniques. We're continuing to look at the WISE archival data. There's a wonderful, wonderful amount of information there. Korean master student Woo-Suk Park is leading that effort. And we've been doing ALMA work, mostly monitoring and a little bit of follow-up, and that's part of UVic PhD student Logan Francis's PhD work. And then finally, we're preparing for the future of far infrared space telescopes, both Speak and Origins, which will have fantastic ability to monitor or follow up these sources. And then as a final slide, let me just point out that this is really important work for understanding the telescopes as well as for doing our own science. When you're trying to care about, when you care about calibration like we do, the first thing you do is you test to see how well the observatory is doing its calibration. You may remember that at 850 microns, we were able to show that the JCMT only gets you a relative calibration of 8 to 10%, and we had to do more work to get better. Well, with ALMA, you expect to get to about 10%. We're able to get to 3% by adding our own calibrator sources in along the set that we monitor. But UVic PhD student Logan Francis, in a paper he just submitted, basically has shown that you have to be careful because sometimes ALMA data is calibrated, the calibration is off by 30%. And that's usually because they haven't updated their calibrator source flux measurements. They've taken them, but they haven't got the calibrations in time for when they made the data set. So buyer beware and look for this paper when it comes out. And I'll stop there, put up my final thoughts, and take any questions. Thank you very much.
Thank you, Doug. Excellent talk. Very interesting and fascinating. Please either raise your hand and to ask a question, or you can type the question into the chat window. So we have one question submitted a while back by Gerald. Are there any FU ORI candidates in your fields which show no signs of variability?
So that's a good question, Gerald. So far, what we have been doing is we've actually been looking the other way. We've basically been looking for what sources in our field show variability, and then we go and see whether anything is known about them. And as you saw, there are a few FU ORI candidates. A few of the sources that are varying have been at other times suggested that they were either FU ORI or X ORI or some other type of source that did a larger burst. We have not yet done that careful analysis, but in fact, we really should, and that's part of what we should be working on this summer. It's a bit hard to do because there aren't good compendiums. What you find out is that somebody did a survey of a region, looked at a bunch of sources, and it is all written down in some paper, but you've got to go find the paper. But that collation is really important. I agree with you.
I have a question, Doug. Can you talk a little bit more about your ALMA follow-up? So beyond using the ACA, can you use the full array for looking in more detail at some of these variable sources?
So it's a struggle. So the problem that we have is that we're trying to do very, very good, very high level calibration. And the problem with ALMA with the 12 meter array is that every time you take an observation, you're actually taking a whole bunch of different baselines than the ones you did before. The configuration is different. And so you got to ask yourself, what are you modeling? How much is your modeling affecting how bright you can act, how well you can actually measure things? And this is what Logan is working on very hard. In fact, he'd be the better person to ask when we're all back up at the observatory. You should talk to him about all of the efforts that he's gone. So we're actually using the ACA in part because the ACA keeps itself in the same setup at all times as opposed to constantly changing. Basically, what we're finding is that ALMA is better for us to be used as a follow-up or to try to see what is the structure of the disk, what is the high resolution structure of a source, like we did with EC53. That becomes, at the moment, a better way to do this because it is the envelope we're looking at in the submillimeter, and the envelope is extended. So it's a bit of a hard game. But as time goes on, we'll do better. And we already have some very nice tentative results from the ACA observations that in fact we're seeing things. But that's, again, that's what Logan's working on.
Question from Jim Hesser is or how is the ALMA observatory, if it is, calibration procedure being modified as a result of your recent work?
So, that's a very good question, Jim. So we involved Todd Hunter from the NASC on our paper because Todd had worked with us before, and he is one of the real data reduction, interferometric data reduction black belts. And so he's an excellent on all of this, and he's completely looped into what ALMA does. And he was the one who realized that the reason why one of our observations was so far off in the ALMA calibration was because they had reduced the data quickly after it was taken, but they hadn't updated the brightness of the quasar that is used as a flux calibrator. The data existed, but it actually hadn't gotten in to be updated. And so once we did that, things came to the 10%. Beyond the 10%, it's not clear what you can do other than if you want better calibration, you need to bring your own calibration scheme. And the whole point of Logan's paper was basically threefold, was to warn people about how bad things can be, to give people an idea of what they should be doing if they really care about the process, and to show basically what we know. And there are other bits, because we also found that the calibration across a single receiver can be problematic. And so people like to use single receiver observations from basically one end of the receiver to the other end of the receiver to look for spectral indices. But there's actually some danger in doing that due to the calibration uncertainty of ALMA. Our whole role was to get this to them so that they'd be aware. We'll see what happens next.
Okay, we have a question from Shantanu. Can you constrain whether the inner disk is thick or thin in the protostars that are not varying?
Yeah, I don't think yet we can say anything about the non-varying systems, Shantanu, and I'd love to talk with you more about this because everything I'm doing right now is from the observational domain, and what I really need are some theoretical ideas of what people think should be occurring so we can see whether or not they're consistent or inconsistent. So I don't know. The sources that aren't varying, our argument would be that the accretion is going through that inner disk smoothly, or if it's not smoothly, the amplitude is low, meaning the amplitude is less than, let's say, 10% in the submillimeter, which is sort of like 30% or so, 40% in the optical. So it's basically saying that the accretion rate is smooth. But whether that's telling me that the disk is thick or thin, I don't know. It's just telling me that the material is able to accrete smoothly. So what I really need is to connect it back to, we need to connect it back to theoretical models to try to understand what would be expected there. So let's talk offline. If you got ideas, please email me.
I don't see any. Oh, there's another question from Gene Malone. Sorry. Could you clarify why EC53 has such a short period compared to the other variable protostar sources you found?
I wish I could, Gene. What it is it is a unique source, and so far we found no other source like it. All of the other sources that are in our survey that we think we're finding timescales, I hate to call them periods, but we're finding timescales. The timescales we're finding are longer than the survey, so we can't even say that they're periodic. All we say is that we're measuring a timescale for some type of a variation. So the question is, why is EC53 so special? So some people like the notion that maybe there really is a tight in binary there, and that's what's keeping it regular as opposed to just varying on longer timescales. But I don't think we know. And again, I think we need the theorists to explain when they might expect. It is accreting at a high accretion rate, and so maybe that has something to do with it. But no, I can't tell you anymore other than to say that it's a wonderful source to be looking at. And I'm hoping that we can expand with the CCAP prime telescope, when it comes online, I'm hoping we can expand our survey by another factor of 5 or 10 sources times in sources, so that we can have a better idea of whether this is really unique or just rare. But I wish I understood. It's a very good question.
I'll just comment from my background is, and when I looked at that light curve of the period, it just reminds me of a, late type kind of Myra type variable rather than a, that's what it looks like if you just looked at the light curve in the period.
Right, but if you, but I don't think your Myra type variable has a color plot like a color plot. That
No,
with
I don't.
variation. Yeah.
Okay, well, thank you again, Doug. Thank you, everybody, for attending. I'll just point out that next week's talk is by Sarah Ellison from UVic, talking about gas star formation in the nearby universe with something called the ALMA Quest survey. So some more exciting results from the ALMA observatories. Okay, and stay safe, everybody, and have a good Canada Day on Wednesday, and we'll hope to see you a week from today. Goodbye.
Thank you, and thank you everybody for listening.